September 14, 1940. Henry Ford stood in the Rolls-Royce factory in Derby, England, watching skilled craftsmen hand-assemble the Merlin engine. Each engine took over 400 hours to build. Ford, the man who had revolutionized automobile production with assembly lines, watched this medieval process with growing frustration. The British were desperate. The Battle of Britain was raging overhead. Spitfires and Hurricanes were being shot down faster than Rolls-Royce could build replacement engines. They needed American mass production. They needed Henry Ford. The Rolls-Royce executives made their pitch: license the Merlin design to Ford. Use American mass production to build thousands of engines. Save Britain from Nazi invasion. Ford listened, walked the factory floor again, examined the blueprints, and gave his answer. No. It was too complex, too many hand-fitted parts, too much precision required. Ford built cars for farmers. This was jewelry for the sky. The British were stunned. Ford was their best hope, the biggest, most capable manufacturer in America. And he had just walked away. Britain was alone, and the engines that powered their only defense were being built by craftsmen one at a time, while Germany's Daimler-Benz factories were churning out thousands. This rejection should have been a disaster. Instead, it led to one of the most important business deals in military history: a $9 million licensing agreement that would produce 55,000 engines, transform the American Mustang from a failure into a war winner, and ultimately help destroy the Luftwaffe. This is the story of how a desperate British government convinced a luxury car company to build the world's most advanced aircraft engine, and how that engine became the heart of Allied air power. The Rolls-Royce Merlin was not just good, it was extraordinary. A V12 liquid-cooled engine that produced over 1,500 horsepower in its early versions and over 2,000 horsepower in later models. It powered the Supermarine Spitfire, the fighter that won the Battle of Britain. It powered the Hawker Hurricane, which actually shot down more German aircraft than the Spitfire. It powered the Avro Lancaster, the heavy bomber that carried the war to Germany's industrial cities. And eventually, it would power the North American P-51 Mustang, turning a mediocre fighter into the aircraft that escorted bombers all the way to Berlin and back. The engine's secret was its two-stage supercharger. Most engines in 1940 struggled at high altitude. The air was too thin. Power dropped dramatically above 15,000 feet. The Merlin's supercharger compressed the thin air, force-feeding the engine, maintaining power all the way up to 30,000 feet where the bombers flew. This gave British fighters a critical advantage. They could climb higher, fight longer, and maintain performance where German engines gasped for oxygen. But in September 1940, Rolls-Royce could only build about 1,500 engines per month from 3 factories: Derby, Crewe, and Glasgow. They were working 24 hours a day, 7 days a week. Skilled workers were sleeping on factory floors between shifts. They had optimized every process. And it wasn't enough. The Battle of Britain was consuming engines at a terrifying rate. Combat damage, mechanical failures, crashes, training accidents. The Royal Air Force needed 3,000 engines per month just to stay even. And that was just for the fighters. Bomber Command needed thousands more for the Lancaster. The mathematics were brutal and simple. At current production rates, Britain would run out of fighters before Germany ran out of bombers. Meanwhile, Germany's Daimler-Benz factories were producing over 2,000 aircraft engines per month. Junkers was producing another 1,500. BMW was adding 1,000 more. Germany's total aircraft engine production was approaching 25,000 per year. Britain's was 18,000, and Britain was fighting alone. France had fallen. The Soviet Union had signed a non-aggression pact with Hitler. America was officially neutral. The only thing standing between Nazi Germany and total victory in Europe was the Royal Air Force. And the Royal Air Force was powered by an engine that was being built too slowly by craftsmen who were already working themselves to exhaustion. The British government understood they needed American industrial capacity. The United States had the factories, the machine tools, the engineering talent, and most importantly, the automotive industry that understood mass production. Henry Ford was the obvious choice. Ford Motor Company was the largest automotive manufacturer in the world. Ford had invented the moving assembly line. Ford had proven that complex mechanisms could be mass-produced by semi-skilled workers using standardized parts and specialized machinery. If anyone could take the hand-crafted Rolls-Royce Merlin and turn it into a mass-produced weapon, it was Henry Ford. But Ford said no, and his reasoning was actually sound from a manufacturing perspective. The Merlin was designed by engineers who thought in terms of craftsmanship, not production. Every engine was slightly different. Parts were hand-fitted, filed, adjusted until they worked perfectly together. Tolerances were incredibly tight. Some measurements required precision to within 1/10,000th of an inch. The blueprints were in imperial measurements but used British standard threads and fasteners that were different from American standards. There were over 8,000 individual parts. Many were machined from solid billets of aluminum, steel, or bronze, creating enormous amounts of waste. The supercharger alone had over 400 components and required specialized knowledge to assemble correctly. Ford's engineers calculated it would take 18 months just to convert blueprints to American standards, design the tooling, and set up production. Then they would need to train workers. Then they would need to debug the inevitable problems. Ford estimated they might be producing engines in meaningful numbers by late 1942. By then, the war might be over. Britain might be invaded. The whole project could be wasted effort. So Ford walked away. He went back to America and focused on building jeeps, trucks, and eventually bombers. But Britain was still desperate, and they still needed American engines. The British Purchasing Commission started approaching other manufacturers. Chrysler said no. General Motors said no. Studebaker said no. They all gave the same answer Ford had given. Too complex, too difficult, too risky. Then the British approached Packard Motor Car Company of Detroit, Michigan. Packard was not Ford. They didn't build millions of cars. They built about 40,000 luxury automobiles per year. Packards were expensive, beautifully engineered, hand-assembled cars for wealthy customers, which actually made them perfect for this job. Packard's engineers understood precision. They understood tight tolerances. They understood complex mechanisms. And they understood how to make things that needed to work perfectly every time. Packard's president, George Christopher, looked at the Rolls-Royce blueprints and saw something Ford had missed. He saw an engine that was actually designed very logically. The complexity wasn't arbitrary. Every part had a clear function. The tight tolerances were necessary for performance, and most importantly, the engine was modular. It could be broken down into sub-assemblies: cylinders, crankcase, supercharger, accessories. Each sub-assembly could be manufactured separately, tested independently, and then brought together for final assembly. This was actually perfect for American mass production methods, but it would require a complete rethinking of how the engine was made. In April 1941, Packard signed the licensing agreement. Rolls-Royce would receive $9 million. In exchange, Packard got complete access to all Merlin blueprints, engineering data, metallurgical specifications, and manufacturing processes. Rolls-Royce would also send engineers to Detroit to assist with production setup. $9 million was an enormous sum, equivalent to about $180 million today. For a company Packard's size, it was a huge financial risk. They were betting their future on their ability to mass-produce an engine that Henry Ford said couldn't be mass-produced. The first challenge was the blueprints. British engineering drawings used imperial measurements, but with British standard threads, which were different from American standard threads. A 3/8 inch bolt in Britain was not the same as a 3/8 inch bolt in America. The thread pitch was different. Packard engineers had to convert over 8,000 part drawings, choosing between keeping British standards, which meant importing fasteners from Britain, or converting to American standards, which meant redesigning parts and getting Rolls-Royce approval for every change. They chose conversion. It took 6 months. Every single drawing was redrawn. Every tolerance was checked. Every material specification was verified against American steel and aluminum grades. British aluminum alloy designations didn't match American designations. Packard metallurgists had to test samples, analyze composition, and find equivalent American alloys that would provide the same strength and heat resistance. The second challenge was tooling. Rolls-Royce built engines using general-purpose machine tools operated by skilled machinists. Each cylinder block was individually machined. A skilled worker would set up the machine, carefully align the workpiece, make test cuts, measure, adjust, and then machine the final part. It took hours per part. Packard designed specialized machinery. They created dedicated production lines where each machine performed one specific operation. A cylinder block would move down the line, and at each station, a different machine would drill, bore, mill, or tap. The machines were set up once by skilled tool makers, then operated by semi-skilled workers who simply loaded parts and pressed buttons. This was Henry Ford's vision applied to aircraft engines. The third challenge was quality control. Rolls-Royce relied on experienced engine builders who could hear when something was wrong, feel when tolerances were off, and know instinctively how to fix problems. Packard created measurement systems. They built gauges for every critical dimension. They trained inspectors to use micrometers, bore gauges, and no-go gauges. Every part was measured. Every measurement was recorded. Parts that were out of tolerance were scrapped immediately. No hand fitting, no adjustments. It either met specification or it was garbage. This created enormous waste initially. Packard scrapped over 40% of parts in the first production runs, but it also created consistency. When an engine left the Packard factory, it was guaranteed to be within specification. The first Packard-built Merlin, designated V1650, came off the line in August 1941. It was shipped to Wright Field in Ohio for testing. Army Air Force engineers tore it down completely, measured everything, and compared it to a British-built Merlin. Their conclusion was stunning. The Packard engine was actually built to tighter tolerances than the Rolls-Royce original. The British engine had variations between parts because of hand fitting. The Packard engine was absolutely consistent. Every cylinder was identical. Every tolerance was exact. The American engine was mechanically superior to the British engine it was copied from. But there was a problem. It didn't make quite as much power. The British engine produced 1,510 horsepower. The Packard engine produced 1,490, 20 horsepower short. The problem was the supercharger. Rolls-Royce superchargers were hand-assembled by specialists who had decades of experience. They knew how to shim the gears, adjust the clearances, and optimize the flow. Packard's superchargers were assembled by workers with 6 weeks of training following written procedures. They were consistent, but they weren't optimized. Packard engineers brought in British supercharger specialists. They studied what the British craftsmen were doing. They measured everything. They discovered that the British were actually compensating for minor variations in castings by adjusting how parts were assembled. Packard couldn't do that with mass production. Instead, they went back and improved the castings. They made the supercharger housing more precise. They tightened tolerances on the gears. They redesigned the impeller with better aerodynamics. By December 1941, the Packard Merlin was producing 1,520 horsepower, more than the British original. And they were building 100 engines per month. By June 1942, production hit 500 per month. By December 1942, 1,000 per month. By mid-1943, Packard was producing 4,000 Merlin engines per month. More than Rolls-Royce's 3 British factories combined. The engines went everywhere. Britain took thousands for Lancaster bombers being built in Canada. The Lancaster used 4 Merlins. Canadian production of Lancasters was limited by engine availability. Packard Merlins eliminated the bottleneck. Canada built over 400 Lancasters powered by American engines. But the most important use of Packard Merlins was in the North American P-51 Mustang. The Mustang had been designed in 1940 as a fighter for Britain. It used an Allison 5 1710 engine. At low altitude, the Mustang was fast and handled beautifully. But above 15,000 feet, the Allison engine lost power dramatically. The Mustang became slow and sluggish exactly where the bombers flew and where the fighting happened. It was a beautiful airframe with the wrong engine. In 1942, a Rolls-Royce test pilot named Ronnie Harker flew a Mustang and immediately recognized the problem. He wrote a memo suggesting that someone try installing a Merlin engine in the Mustang airframe. The idea seemed obvious in retrospect. The Mustang had the most aerodynamically efficient airframe of any fighter. Low drag, laminar flow wing, clean lines. The Merlin had the best high-altitude performance of any engine. Put them together. In October 1942, North American Aviation installed a Packard Merlin 5 1650 in a Mustang airframe, creating the P-51B. The results were extraordinary. At 30,000 feet, the Merlin-powered Mustang was 100 miles per hour faster than the Allison-powered version. It could outclimb, outrun, and outfight anything Germany had. And because of the Mustang's efficient airframe and the Merlin's fuel economy, it had range. With drop tanks, the P-51 could fly from England to Berlin and back, escorting bombers the entire way. This solved the single biggest problem facing the American daylight bombing campaign. Before the Merlin Mustang, American bombers were being slaughtered over Germany because they had no fighter escort for the deep penetration missions. German fighters would wait until the short-range P-47s turned back, then attack the defenseless bombers. Loss rates were catastrophic. The entire strategic bombing campaign was on the verge of being called off. The P-51 Mustang with the Packard Merlin engine changed everything. By spring 1944, Mustangs were escorting every bomber mission. German fighter pilots, who had been able to attack bombers with impunity, now faced aggressive American fighters that could outperform them and had enough fuel to chase them anywhere. The Luftwaffe was destroyed, not primarily by bombers, but by Mustangs. By the end of the war, P-51 pilots had shot down nearly 5,000 German aircraft. They had established air superiority over Germany, and it was all powered by an engine that Henry Ford said couldn't be mass-produced, built by a luxury car company that proved him wrong. Packard produced 55,000 Merlin engines between 1941 and 1945. Rolls-Royce produced about 113,000 in Britain. Total Merlin production from all sources was approximately 168,000 engines. The $9 million licensing fee that seemed so expensive in 1941 ended up being the best money Britain ever spent. That investment bought American industrial capacity. It bought 55,000 engines that powered fighters and bombers that won the air war. It bought the technology transfer that allowed American engineers to improve British designs. And most importantly, it bought the P-51 Mustang's transformation from a mediocre low-altitude fighter into the aircraft that escorted bombers to Berlin and destroyed the Luftwaffe. The economics are almost impossible to calculate. How do you value an engine that helped win a war? How do you measure the return on investment for technology that saved Western civilization? If the Merlin hadn't been mass-produced, if Britain had been limited to Rolls-Royce's 18,000 engines per year, the Lancaster bomber offensive would have been smaller. The Mustang would never have reached its potential, and the strategic bombing campaign might have failed. The cost of that failure, measured in lives, treasure, and freedom, would have been incalculable. The Packard Merlin story is a lesson in how industrial capacity wins wars. Britain had the engineering genius. Rolls-Royce had created a masterpiece engine. But genius and masterpieces aren't enough when you're fighting for survival. You need production. You need thousands of engines, not hundreds. You need the ability to replace losses, to equip new squadrons, to overwhelm the enemy with material superiority. America provided that capacity, but it wasn't automatic. It required British willingness to share their most advanced technology. It required American willingness to take on an enormously difficult manufacturing challenge. It required engineers on both sides of the Atlantic to work together, to solve problems, to trust each other. And it required a company, Packard, that was willing to bet its future on being able to do what the biggest automotive manufacturer in America said was impossible. The Merlin engine remained in production until 1950. Packard continued building engines for several years after the war ended. The final version, the V1650-9, produced over 1,800 horsepower. These engines powered the fastest piston engine fighters ever built. And today, 80 years later, Rolls-Royce Merlins and Packard Merlins are still flying. Vintage aircraft enthusiasts maintain Spitfires, Hurricanes, Lancasters, and Mustangs, and those aircraft are powered by engines that were built in Derby or Detroit between 1940 and 1950. When you hear a Spitfire at an air show, when you see a Lancaster flying overhead, when you watch a Mustang race across the sky, you're hearing the sound of an engine that won the Second World War. And chances are, that engine was built in Detroit by a luxury car company that took on the challenge Henry Ford refused. The engine that was too complex to mass produce, the engine that ended up being produced by the tens of thousands, the engine that powered Allied victory in the air. The Rolls-Royce Merlin, built by Packard, paid for by a $9 million bet that Britain made when they had no other choice. It was the best $9 million ever spent.